In this video, I'll give an intuitive and very easy to understand explanation of how do you measure the performance of different machine learning classifiers, especially when you are dealing with imbalanced dataset. So we'll touch on a lot of technical concepts like accuracy, precision, recall, confusion metrics, F1 score, calculating area under the curve of ROC, and much more. And I'll try to simplify all these fancy looking concepts in the simplest possible terms. So let's say that you have trained a machine learning classifier. You take a bunch of independent variables to calculate a binary output, 0 or 1. Since in this video I want to emphasize on how you deal with imbalanced data, you're trying to predict fraud in the banking transactions. So the output of your model would be if it is fraud or not. And the input variables could be what is the amount of the transaction, when it's happening, what is the distance from the last transaction, etc., etc. So there could be multiple independent variables which you can use. And while training the model, you have seen that there are about 1 million zeros, which is non-fraud transactions, and then you see one fraudulent transaction. So in a nutshell, the ratio between non-fraudulent transactions and fraudulent transaction is 1,000,000 to 1. Now the problem with just measuring accuracy is that even if your model for your entire test set predicts that it is a non-fraudulent transaction, it will still be 1,000,000 times right and only one time wrong. So your model's accuracy would still be 0.999999%, which is almost 100%. So now on paper, though you'll get an accuracy of 100%, but your model is actually garbage. It is totally trash, totally useless, because it will never alert you for any fraudulent transaction, and for every incoming transaction, it will just say that it is a non-fraudulent transaction. So if you have set up some alerts based on if you see high probability of fraud in any transaction, it should alert you. That system will never alert you because it will never see high probability, because your classifier is always saying it is a non-fraudulent transaction. So what can we do about this kind of scenario? Well, the first step is that we create a confusion metric. So though the name is confusion metrics, but it is a very simple concept and you can draw it in just a couple of seconds. So what you have to do is you have to draw a 2x2 table like this, where in top you have predicted yes and predicted no, and then on the left you have actual yes and actual no. By yes, I actually mean that the value would be 1 and no would be 0, and same here. And then you look at the model's performance on a test dataset, and then you fill out these boxes in this table. So in this box, you'll fill out what is the case where the actual value is 1 and the model also predicted 1. How many cases the actual value was 1, but the model said no or 0. For how many cases the actual value was 0, but the model predicted 1, and for how many cases the actual value was 0 and the model also predicted 0. So as you can see, these would be the correct answers where the actual value was 1 and the model also predicted 1, or the actual value was 0 and the model also predicted 0. And these would be the wrong cases where the actual value was 0, but the model predicted yes, or where the actual value was 1 and the model predicted 0. So you want to maximize values in this quadrant and minimize the values in this diagonal. And just by creating and looking at this confusion metric, it will give you a very good idea of how good or bad your model is doing, especially for minority classes for which you do not have a lot of examples in your training as well as test dataset. But then the question is that how do you report to someone how good or bad your model is doing? And also, if you have to make an adjustment on the probability threshold based on which if you decide it is a 1 or 0, then how you can tweak it. So because of these two issues, we calculate two other values, which is precision and recall. Now the way they are calculated is that precision is basically true positives divided by true positives plus false positives. Now what is a true positive? A true positive is basically this value right here. Positive here basically means that what if the model said it is a class 1 or 0, and this basically tells if it is a true prediction or false. So we can see that the model predicted positive and it is a true prediction. The model predicted positive here, but this is false prediction. The model predicted negative here, so it is negative, but it is false because the actual value was 1. And the model predicted negative here, but it is true because the actual value is also 0. So this is how we calculate precision. Similarly, the formula for recall is true positive divided by true positives and false negatives. Now, if you try to memorize this formula and try to see that how it maps to this table, and then try to do the math in your head that what does precision and recall actually mean, you will never be able to understand it. So let me give you a very intuitive, easier explanation for both of these. So once you understand that, then you never again have to run into a confusion of what is precision and what is recall. So let's look at recall first. Now, what does word recall mean? It is basically related to memory, and it means that if you have seen something or if you have memorized something, how well are you able to recall that? So recall in this case is also that. It basically means that of all actual ones, how many did you correctly classify it? So it is basically asking of all the ones in the data, how many were you able to correctly recall? So this is where the word recall comes in, and this is what it intuitively means. So let's say if your actual data had 10 ones, then of all those 10 ones, how many your model was also able to say that these were ones. And once you understand this intuitive explanation of this, you can also step back and then try to derive the formula for this, which is, we can see that the denominator here is all the actual ones. So it is basically TP, and let me draw the confusion metric again so that you can see what I'm saying. So we want to see what are all the actual ones. So we can see this is this part here. So this is all the ones. And then we want to say how many did you correctly classified as one. And this is this part here. So it becomes, this is the formula. Now precision word, it comes from precise, right? Which means that whatever you're telling, how correct or good that information is. So basically the intuitive definition of precision is that all the ones which you have predicted, how many of them were actually ones? Of all the examples where you have predicted as one, how many were actually ones? And by understanding this intuitive explanation of it, you can again go back to your confusion metric and drive the formula for this. That we can say that for all where prediction is one, and this is where the prediction is one, so we can see that the denominator would be TP plus FP, and the numerator would be what subsection of this was actually true. It is this part. So it will be this. Now this precision and recall, they are very important concepts whenever you're trying to use a classification machine learning algorithm, and especially when you're dealing with imbalanced data set, which for practical cases is almost always true. I've been into this profession for 15 years, and I don't really remember a time that when I looked at the data and I found the distribution of zeros and one almost identical. It is always skewed either towards 0 or 1. So whenever you train a machine learning algorithm to classify that, it is super important that you understand what is the precision of your model, you understand what is the recall of your model. It is also a very important interview question. So understand the intuition behind precision and recall instead of just memorizing the formulas, which would do you no good. So I hope the explanation here is useful. Recall is based on memory. It is basically saying that all the ones out there, how many were you able to correctly classify? And precision is related to how precise your outputs are, which means that of all the ones which you have predicted, how many actually were right or precise answers. And once you understand the intuition, you can definitely write the formulas as well. Now precision and recall are slightly opposite of each other. So in a model, when you're trying to make the precision number high, you would see that the recall would be dropping. And same is true for recall. If you try to make the recall high, you'll see that the precision numbers would be dropping. So then the question is that which should you prioritize, recall or should you prioritize precision? Let me give a very loose guidance for that. If there are scenarios where you don't want to miss out on any positive event, for example, credit card fraud detection, then you should try to prioritize recall. So in other words, if the cost of inaction is high, then you should go for precision. And similarly, if the cost of action is high, for example, if you're trying to train a model in which case the tax department should do a detailed audit of someone. Or let's say if you're working in a marketing department of a company and you want to send out direct mail where the cost of each mail is $5 or something. So you only want to send it to people where you have high probability that they will buy from you. So since the cost of action is expensive, so in that case you should try to prioritize precision. Now there would be some scenarios in which you do not have a very clear preference or clear understanding of if the cost of action or inaction is very high. In that case, the general industry practice is that we sort of take an average of these and then try to see what gives us the best result. And this average is called F1 score. Let me explain what it means. To better understand F1 score, let's look at this chart. So let's say you have this chart, and on the x-axis you have different thresholds based on which you make a decision of if the class is 1 or 0. So the lowest value is 0.0 and the highest value is 1.1, and this is in the middle, and this is the threshold. And on the y-axis you have value between 0 and 1, and this basically tells you that how your model's precision and recall is doing as you change the threshold for decision. So let's look at recall first. What you would see is that your recall would be 100% when the threshold is 0, and your recall would be near 0 when the threshold is 1. It will basically have a curve like this. So this is precision. So now when you look at recall, it will have an opposite trend. It will go like this, let's say. So as you can see that when the precision is high, the recall is low, and when the recall is high, the precision is low. So then the question is that what threshold should you take? Now, if you have a clear understanding if the cost of action or inaction is very high, then you can definitely, based on some business use case, make the decision. But if that's not a clear priority, then you basically have to find a balance between both. Now, one very intuitive and easy option is that you just take the average of these two, and wherever that average is high, you just take that value. Now you can take the normal mean, but scientists have discovered that if you take the harmonic mean, it has an added benefit that it penalizes the extreme values more. So that's why when we take the mean value or the average, it is not the normal mean. Instead, we take the harmonic mean. And that harmonic mean is called F1 score. And if you plot it on this, it will go something like this. And then it drops down. So once we have plotted these charts, then we can see that at what point is the value of this F1 score maximum, which we can see is this point for this particular data, which could be, let's say 0.4, and then we take this as our threshold for deciding if the class belongs to 0 or 1 class. Now there is another evaluation method which works even better than F1 score. It has a very funny looking name, so let's look at the name first. This is called Receiver Operating Characteristic, or ROC curves. To explain why it has such funky looking name, let me explain the origin of this. In the World War II, fighter jets were relatively a new invention, and to minimize the damage from enemy's fighter jets, radars were invented. Now, countries wanted to know how well their radars are performing in terms of identifying and alerting if they see an enemy fighter jet. And to measure the performance of these radars, this receiving operating characteristic curves were introduced. So receiver here basically means radar, and operating characteristic basically means its performance. So receiving operating characteristic or ROC curves were introduced to measure the performance of radars, but since then they have been used to measure the performance of any other system, which gives a binary output of if an event is happening or if it is not happening. And as you can guess from the origin story, two inputs which radar gets: one, that there is no enemy fighter jet present, and second, there is an enemy jet present, is very imbalanced. 99.999% of the time there won't be any fighter jet present, and only it's 0.001% of the time that the enemy jet will be presented. So these ROC curves are specifically designed to help ascertain the performance of systems where the class is very imbalanced. And the best thing about these is that they give you one number which you can use to measure and evaluate the performance of your model and compare it against other models. And also based on this, you can help decide what should be the right threshold you should use to define if an outcome should be 1 or 0. So now let's see how these ROC curves are created. On the x-axis, you have false positive rates, or In other words, where the prediction is 1 and actual is 0, and on the y-axis you have true positive rate, where the prediction is 1 and also the actual value is also 1. And now one by one, you take different thresholds, starting all the way from 0, and then by looking at 0.1, 0.2, till you reach the final threshold, which is 1.0. And based on each of these thresholds, you will see that some dots will be plotted on this line. Now, in the case that the model performance is totally random, the false positive rate and the true positive rate would be almost equal for pretty much all the thresholds you test. So from 0 all the way to 1.0, as you use different thresholds for predictions, you'll see the data point will be distributed at equal distance from both of these lines. So it'll be a straight line, something going like this. And this would be the case when the model prediction is as good as random predictions. Now, just like when we were evaluating linear regression, we used the mean value of the output variable as the benchmark against which we compared the model's performance. Just like that, in this case, we use this diagonal line to use as the benchmark against which we will evaluate the model performance. Now, in an ideal world, when the model performance is very good, you should see a curve which goes like this. It touches the upper left corner. But in most practical cases, the curve would be somewhere in between. So it will be going something like this. Now from this curve, you can tell that this model's performance is better than this diagonal line, but to come up with a number which can tell you how better it is, we calculate the area under the curve. So a simple explanation for this is that if this is the total area, and if this diagonal line is dividing it into half, then we know that the area under the curve for this diagonal line would be 0.5. Because this diagonal line is dividing in half this entire surface area. And when we measure the area under this curve, it would be all the area which is here, represented by these horizontal lines. So now as we know that the area under this diagonal line is 0.5, we can calculate with the help of math that what is the area under the prediction line. And let's say in this case it is 0.7. Now by looking at these two numbers, 0.5 and 0.7, we can tell that the model is relatively better as compared to this prediction baseline, which is just as good as a flip of coin. And the best part is that this number which we get, it is very insensitive to the imbalance in the class distribution. So even if the class distribution is highly imbalanced, this will tell you how good or bad this model is. And since all the dots on this line, what is the threshold used to create that dot, you can look at this line and based on what is the right amount of true positive rate or false positive rate you want in your model, you can pick a threshold based on that. So if you want to minimize the amount of false positives, for example, if you are using this model to send out direct marketing campaigns or to identify who the tax department should audit, you can use a higher threshold. And in case you want to maximize the true positives, for example, in the case of fraud detection, or in the case when the radars are trying to detect if there's a presence of enemy fighter jet in the airspace, then you can use a lower threshold based on this analysis. I hope you found the explanation of all these concepts simple and easy to grasp. If you want to see more videos explaining other machine learning algorithms, just like I explained these ones, please let me know in the comments below. Thank you so much for watching.